Flux through a surface is not an easy thing to do. It's a complicated process and it involves parameterizations and there's a bunch of steps. So I think I've got a couple of really solid examples here. There's a quick discussion about what it means to orient a surface, and then, very little theory, just jump straight in and work out some, what I think are meaningful examples. So you're solving some kind of flux problem, and there's always going to be one part of the problem that indicates which way the surface is oriented. So it's going to say something like in the positive z direction, or away from the xy plane, or outward, or something like that. So I'm imagining a scenario here where in the problem it said something like away from the xy plane, and I'm imagining the xy plane as being that plane down there. So what you do is you look at the parameterization and you ask yourself, which way would that point, would the little point move if I increased u? And that will give you some vector. Let's suppose that it points in this direction. So that would be the partial u derivative of the parameterization. And then suppose that you ask the same question and you got some other vector like that, like r sub v. Now, at this point, we're trying to say we want the vector to be pointing away from the xy plane. So that's this vector that points in this direction right there. So now you got to use the right-hand rule. I'll draw the hand in a second, but hopefully you can see that in this case, you would need to do r sub u cross r sub v. Let me draw the little hand picture. This will take me an hour. Okay, that's the best right-hand rule drawing I could. What I'm saying is that if you ever pick backwards, it's usually obvious just by looking at the normal vector that you've chosen the wrong way. It's not a big deal. Your choices to fix it are, you can either switch the order and do r sub v cross r sub u, or you can just stick a negative in front of it, and basically that would be giving you that normal vector that points into the surface right there. So this actually leads us to a really kind of cool, interesting math question, which is there always only one answer to this question? Is it possible that there could be a surface that doesn't have an orientation? So the short answer is no. Not every surface has an orientation. Here's an example of a surface that doesn't. It's called a Mobius strip. That's kind of a cool thing. So one way that you can think of orientable, or if it has an orientation, is to imagine something like a piece of paper. Okay, and let's suppose that I had a piece of paper and I wrote A on this side, and then, I flipped this piece of paper over and I wrote B on the other side. Then this is an example of a surface that is orientable. It has two sides. And one way to see that is if I had the piece of paper here and I wrote A on this side, and I started drawing a normal vector that pointed in this direction, then I can move that normal vector around. Like I can move it over here, and I can move it over here. But unless I go across the boundary of the surface, kind of wrap around to the other side of the surface, all of my normal vectors are all pointing in the same direction, right? I never had a normal vector that pointed in the opposite direction. So let's just look at this Mobius strip, and it is going to fail this kind of setup here where we imagine a surface that has two sides. So let's start, and let's suppose that I wrote an A right here on this side of the strip. And I have that. I should mention how this is made first. How do you make these things? So what you do is you start with a ribbon or a piece of paper or something. And then you give it a little twist like this. You see I've just kind of given it a little twist there in the middle. All right. And then you bring it around and you connect that side to that side, and that's how you make this Mobius strip. So let's suppose that I named this, can you see, see here, this would be side A, and then now over here, this would be side B, and then I'm connecting them together. That's what breaks this. So let's just kind of prove it using our normal vector thing. So this is supposed to be side A right here, right? So I have a normal vector that's kind of pointing in that direction. And then as I kind of twist around, right, I'd kind of be going like this. And then up here, I guess it'd kind of be going like this, and then right here it'd be going like that. And then you can see that I'm on the back side of the strip right there. So I'm coming out those sides right there, and then I'm on the back side, so that connects to this piece right here. still going around, still going around, still going around, still going around. And now, boom, look, there it is right there. There's the same normal vectors. And I started on one side and I just sort of traced it around the strip, and I ended up on the pointing in exactly the opposite direction. So this means that the Mobius strip doesn't have an orientation. It isn't orientable. There isn't like one side of this. So like I can hear you panicking in your head, and you know, this isn't like an issue that comes up in like a calculus class if you're trying to calculate flux through a surface. I'm just pointing out that it is possible to ask a nonsense question. I could never calculate the flux through the Mobius strip because I could never pick which direction the normal vector is going, right? I mean, if I declared the normal vector to be going in this direction, then, you know, I just move it around and it's also going in that direction. So it like doesn't even make sense. So it's sort of possible for for there to be a flux question that is like not a well-defined question. This is just kind of a quick theoretical point there. You know, it doesn't ever like come up when you're solving a calculus 3 level problem. I just want to point it out that this isn't always possible. Not every surface has an orientation. Okay, I'm going to solve this flux problem about a cone, and I'll forever remember my students. There's a TV show called Parks and Rec, and there's a game, Cones of Dunshire, and I remember one semester my students were relentlessly teasing me about that show and my math problems. So anyways, pause the video here, take a minute to copy down the problem. Okay, I'm gonna assume that you did that now. Okay, so what we're doing is I want the normal vectors to be oriented away from the z-axis. So in this problem, all our normal vectors need to be pointing out right there. And we are between these two values of the cone. So the first thing that we need to do is set up a parameterization. Okay, so I think it's pretty obvious that we're going to use some type of cylindrical coordinates in order to parameterize this surface. Now, if z equals 1, I'm going to have 1 equals 10 minus r. So this is going to give me r equals 9. And if I have z equals 9, then I will have 9 is equal to 10 minus r. So that's going to give me r equals 1. So that basically what I'm calculating here is the range of values for r. I think also it's pretty clear to see that theta is in between 0 and 2 pi. And just to be clear, what that's going to look like is the shadow of this is the portion of the surface that we're trying to calculate right there. So the shadow of that in the XY plane is this kind of annulus shape or washer shape right there. So it's got that hole in the middle of it because we chopped off the top of the cone there. All right, brilliant. So we've got our range of parameters, and I've got F here. And I've got F here. So the next thing, I mean, we're pretty much ready to go. I just need to start calculating R sub U, R sub V in order to make my normal vector point away from the z-axis. I've done a bad job of naming my letters here because R is both the parameterization and R is the radius. So I'm sorry, but I swear you guys are grown-ups. You can tell the difference. When I put the little vector over the top of it, I mean the parameterization, and just regular R is like the variable that means radius. I could use U and V, but whatever. All right, so now what I need to do, I'm imagining them there at one of these points, and I need to decide which direction do these vectors go in. So I want to calculate the partial derivative of this with respect to the radius. So what that question means is, which way do I need to move in order for the radius of these circles to increase? Think about it. If I move in this direction right here, that will cause the radiuses to get bigger and bigger and bigger. Okay, now which direction do I need to move in order to cause theta to increase? So theta opens from the x-axis towards the y-axis, so theta opens in that direction right there. So that means this way right here is r sub theta. So there's r sub r, and there's r sub theta right there. So let's just right-hand rule this. R sub r cross r sub theta will give me an outward normal vector. Set up my little cross product here, and now I'm going to calculate some partial derivatives. So I'm just taking partial derivatives of this thing with respect to the variables. So I'm going to take an r partial derivative. I get cos theta. And then I'm going to take an r partial derivative. I'm going to get sine theta. Then I take an r partial derivative of that, and I'm going to get -1. Now I'm finding theta partial derivatives. So theta partial derivative of this, I'm getting r, the derivative of cosine is negative sine, so negative r sine theta. Then the theta derivative of that is going to be r cos theta. And then the theta derivative of that is going to be 0. So let me calculate this cross product. All right, I cleaned up the board here. I made a little mistake in my cross product. I ended up with too many cosines, so I'm doing it over again. Everybody's human. We all make mistakes. So let's do this cross product. So first you got to cover up the i's and the j's and the k's, and then this one will be 0, and then it is minus this diagonal. So I am getting for the first coordinate r cos theta. All right, now let's look at this second coordinate right there. So I cross those out. All right, now we've got a lot of negatives floating around in this problem. So let's count the total number of negatives that are present here. So first of all, there's 2. There's 1 there and 1 there. So there's 2 negatives. Then it goes plus, minus, plus. So there's another negative right there from the minus. And then it goes this diagonal minus that diagonal right there. So I have 4 total minus signs. So that means whatever goes in this coordinate is positive. And what I've got here is the major diagonal is cosine times 0, and the minor diagonal is 1 times r sine theta. So I should end up with an r sine theta. That's what I messed up last time in that middle coordinate there. Now for the k coordinate down here, I'm going to cover this one up, right? And that one. So then I'm going to have, hopefully you can see here, r cos squared theta, and then this one, it's going to be minus a negative, so it'll be plus r sine squared theta. So in the end, I'm just going to put an r in that last coordinate. Okay, so you always check this at the end. Remember that our r values are in between 1 and 9. So if you plug in a value for r, you are going to get a positive number in the last coordinate of this normal vector. So what I'm saying is, like, we've got some kind of cone and we're at some point, and our normal vector is going to go over some x amount and over some y amount and then up. So the final answer is going to be some kind of upward pointing vector because I plugged in a positive number for these r values. So actually, when you're doing this whole process, I hear you that it's one of the confusing things is which way to do the cross product in order to get the normal vector to point in the direction that you want it to. And what I'm saying is, once you've done it, once you make a guess and write out the answer, you should actually just be able to look at the answer that you get for the cross product and what kind of values you're plugging into the parameter. And that can serve as like a check to make sure that you've done your cross product in the correct order. If you didn't, just slap a negative sign in front of it and then it will be the correct way. Okay, so the next step here is to substitute all the parameterizations into capital F. So I'm looking at negative x right there. So I'm going to put negative, and then x is r cos theta. So negative r cos theta. And then negative y. So that's going to be negative r sine theta. And then 3z squared. So that's going to be 3 times 10 minus r quantity squared. So now I've got f, and this thing right here is r sub u cross r sub v. So we are really close to having this thing set up. Let me just kind of make room here and set this up. All I did here was I just plugged everything into this equation right there. So I just literally copied down what f was and what r sub u cross r sub v was. What I want to point out is that at the end, I didn't need to put any like Jacobians there or anything. That's kind of the good thing about this like d sigma formula is. This isn't dv or dA or anything at the end of it. So you don't need like any change of coordinates formulas to go at the end. It's just literally whatever your parameters are. All right, so now this is a dot product. The formula has a dot product into it. So what I need to do is just like multiply the x's and the y's and the z's and then add them all up. So I'll do that. Okay, so I worked this out on my little scratch paper over here, and I got like a giant negative number. And that actually does make sense. So guess what? Let's bounce over to CalcPlot 3D. So here I have the surface plotted, and I have not the whole vector field. This is just the vector field in the XY plane, and you can see all those vectors fluxing into the surface there. Let me have it draw a little bit more. The graph gets pretty busy, but let's do our best to kind of dissect this. So there you can see so basically what happens is all these vectors are fluxing into the surface, and then they're tilting up a little bit more as we go up the z-axis. But no surprise, I mean, look at all that inward flux, right? I mean, all those vectors are pointing into the surface. So when we calculated the outward flux, we got a big negative number because it's not fluxing outward, it's fluxing inward. So we got the negative of outward flux. So all this checks out. Yeah, so there it is. Let me do another one. This was fun. Here's another flux problem. So pause the video and write down the problem. Okay, I'm going to assume that you paused the video and wrote down the problem. All right, so first let's try to decipher what this surface even looks like. So here I have z is equal to 4 minus y squared. So this surface is independent of x. And in the zy plane, that's this plane right here, I see a parabola and it's facing down and it's been shifted up 4 units. So I guess it's something like this. And then it's that same parabola copied all the way down the x-axis for x's in between 1 and 0. So let me draw that. So that was fun. I drew a little, I guess it's a parabolic cylinder here. And I came up with this kind of trivial parameterization. Whenever anybody gives me a parameterization gives me an explicit function, I always parameterize it in this trivial way. Now we've got the hard part here. Let's decide which way I need to do the cross product in order to produce an outward normal vector. All right, so the first thing is, actually it's pretty obvious, if I increase z, which way is this point going to move on this surface? It's going to go that direction, right? So that means this right here, sorry, did I say z? If I increase x, it's going to go out the x-axis, so I'm going to move in that way on the surface. So that right there is r sub x. Now, if I increase y, if I'm at this point right there, and I make the y's get bigger, okay, then I am actually going to go down this surface. Can you see how if I go down the surface like that, that actually pushes me farther down the y-axis direction? So r sub y is going to go that way. All right, let's put our thinking caps on and decide, okay, r sub x cross r sub y. I think r sub x cross r sub y. Okay, I drew the little nightmare right-hand rule hand there. I hope you all draw this in your notes. Okay, if you don't know this, if you don't draw this hand, it's automatic F. Not just for you, everyone in the class fails. All right, let me calculate these partial derivatives so I can get this outward normal vector. So I'm taking this parameterization right there, and I am calculating the x partial derivative. So what, 1, 0, 0. All right, now I am going to do the y partial derivative. So I'm getting 0, 1, negative 2y. Okay, cross product coming up. Okay, so this should be pretty easy. I calculated my, so I covered these guys up, right? And I get this. Okay, so there's a bunch of zeros there. So get 0 in the first coordinate. Now I'm covering this one up. So it's this diagonal right there. But remember, the formula goes plus minus plus. So in the middle there, that negative cancels with that. So I ended up with 2y. And then in the k coordinate, you cross those out and you get 1 minus 0 is 1. The next thing we need to do is plug our parameterization into f. So it was z squared, and z is 4 minus y squared. So this is going to be 4 minus y squared squared, because it's z squared, and then x is x, and then negative 4z. So that's going to be negative 4 times z, which is 4 minus y squared. Yay! So now I've got f, and I've got n, so I think I am ready to set up this double integral and find the actual flux of this. So the formula is f dot r sub u cross r sub v, so that's what I have set up right here. And now I need to figure out what the limits of integration are. So I'm integrating over all the parameters that give me this surface. So the parameters are x and y, so all the values of x and y that give me a point on this surface is that rectangle right there. So I've drawn that rectangle over again. And I think it's pretty obvious where I got the x equals 0 and the x equals 1 from. Now, if z is equal to 0, that's the values of y that give me this rectangle right there. So if z is equal to 0, that means 0 is equal to 4 minus y squared. Okay, so that tells me that this rectangle is bounded by y equals -2 and y equals +2. So my y limits are going to be from -2 to 2, and my x limits are going to be from 0 to 1. All right, let me work out this dot product. I worked out the dot product, couldn't stop myself, worked out the whole thing. Right, so I mean, when you do dot product, oh, that's nice, it's 0, that guy's gone. And then this is giving me 2yx here, and then this thing times 1 is just giving me that thing. So then, you know, I did my little work on my scratch paper here. I got a negative 128 over 3. So again, we are getting negative outward flux. Let's just check and make sure that that agrees with our picture. So here I've had CalcPlot 3D graph the surface. I guess my drawing, I drew way longer than it really is. I mean, it's just the x's are just between 0 and 1. Okay, so here is the force field and there is the surface. So I think when you look at it from this direction, you can actually see, can you see right there? The force field is fluxing across the surface inward, right? All these vectors are pointing inward across the surface right there. There you get a pretty good picture from this angle as well. You can see a bunch of vectors that are pointing into the surface. They're kind of pointing down the x-axis and into the surface. So that's why when we calculated the flux, we ended up with a negative answer. So hopefully that these two examples help you calculate any flux problem that you're working on. Just to run through the method one more time. Basically, the setup here is you start with a parameterization and you figure out which way you need to parameterize it to orient the surface correctly. And then plug that parameter, do the cross product to get the normal vector, plug that into the force field, and then just set up your dot product integral. And then from there on out, it's just double integrals in order to spit out the answer. Please let me know if you get stuck or you have any questions.